Imagine discovering that your entire life has been observed through a one-way mirror and you're just now noticing the glass. For 70 years, we've wondered why the universe seems so empty despite containing billions of potentially habitable worlds. We call this the Fermi Paradox, the great, profound silence that surrounds our planet. But what if the silence was never empty? What if it was careful? Right now, something called 3I-ATLAS is racing through our solar system with a chemistry that shouldn't exist, a timing that seems far too convenient, and a behavior that is making scientists whisper uncomfortable and fascinating questions. Stay until the end to discover why this cosmic visitor might just prove that we are being studied by intelligences who prefer to watch from the shadows. The silence of the stars. Picture this. 400 billion stars, 400 billion suns, each one of them potentially warming the worlds of their own. In our galaxy alone, we are talking about the planetary systems that are numbering in the trillions. The rocky worlds, the gas giants, and the moons with the vast subsurface oceans. The mathematics of a possibility stretches far beyond our comprehension, and yet there is a nothing. There is no signal, no message, and no hello that is echoing across the cosmic dark. This is the Fermi Paradox, which was named after the physicist Enrico Fermi, who had posed a deceptively simple question during a 1950 lunch conversation: where is everybody? It is a question that should keep you awake at a night, though tonight we will let it to gently carry you towards a sleep instead. Consider the arithmetic for a moment. Our galaxy was formed roughly 13 billion years ago. The Earth took 4.5 billion years to develop a complex life and just a few million more to produce a species that was capable of sending the radio waves into space. If the similar processes occurred elsewhere, even on just a tiny fraction of those trillions of the worlds, we should be swimming in an alien chatter by now. But we are not. The silence is so profound that the scientists have proposed only the three reasonable explanations. First, an intelligent life might be extraordinarily rare. Perhaps we are the cosmic lottery winners, the one in a trillion accident that somehow stumbled into a consciousness and a technology. It is a lonely thought, but it is statistically possible. Second, maybe the civilizations tend to vanish. They reach a certain level of a development, and then something happens, a nuclear war, a climate collapse, or an artificial intelligence that has gone wrong. Some universal stumbling block that claims every species right before they learn to reach for the stars. The scientists call this the Great Filter, a cosmic sieve that catches the civilizations just as they are getting interesting. Or third, and this is where the things get intriguing, they are out there, but they are keeping quiet. Maybe there is a galactic ethics code, a universal prime directive that forbids an interference with the developing worlds. The zoo hypothesis suggests that we are living in a carefully maintained preserve, which is observed but not contacted. Or perhaps the universe operates under the darker rules, where broadcasting your location is tantamount to painting a target on your world. A speak up and something hungry might come a calling. But here is what most of the people do not realize. The game has changed. We are not just listening anymore. Every night, the automated telescopes sweep the sky, the digital sentinels that are scanning for anything that is unusual, anything that is out of place. The Asteroid Terrestrial Impact Last Alert System, or ATLAS, operates the 4 telescopes across the globe, photographing the entire visible sky every 48 hours. They are looking for the asteroids, of course, the rocks that might threaten our world. But sometimes they find something else entirely. Sometimes they find the visitors from the space that is between the stars. In a recorded history, we have confirmed only the 3 objects from beyond our solar system. The 3 wanderers that originated somewhere else entirely, that traveled for the millions or the billions of the years through the interstellar void, and that happened to pass close enough for us to notice. The first one was discovered in 2017, the second one in 2019, and the third one arrived this year. And unlike its predecessors, this one is behaving in the ways that make the scientists whisper among themselves in the conference hallways, the ways that might offer a clue to the great silence that surrounds us. Tonight, we are going to follow this cosmic visitor on its journey through our solar system. We will examine the evidence with the careful eye of a science, but we will also dare to ask the questions that linger at the edges of a respectable research. Could this wanderer from the dark be a natural? Almost certainly. Could it be something more? Well, that is what makes for an interesting conversation. We will explore the mystery in the 3 acts. First, the arrival and the discovery of our enigmatic visitor, then a survey of the cosmic puzzle that is the Fermi Paradox itself. And finally, we will consider what it might mean for a science, for a humanity, and for our place in the universe if this wanderer carries the secrets from the stars. So, settle back. Let your mind to drift outward past the moon, past the planets, to the space that is between the solar systems, where the ancient travelers make their slow way toward the distant suns. The universe is about to tell us a story. Whether it is a story of an ice and a rock and a natural physics, or something that is altogether more extraordinary, remains to be seen. But either way, the silence of the stars has been broken by the arrival of something that is wonderful and strange. The visitor called 3I-ATLAS. Every few years, if we are lucky, the universe delivers a gift from the cosmic deep. Not that is wrapped in the ribbons, but that is cloaked in an ice and a dust that is traveling faster than anything that is gravitationally bound to our sun should ever move. On July 1st, 2025, one of those gifts arrived. Its name is as bureaucratic as a government paperwork, 3I-ATLAS, which was formerly designated as C2025N1. The 3I means that it is the third confirmed interstellar object that we have ever seen. The Atlas credits the survey telescope that first spotted it, which was scanning the southern sky from Chile with the patient persistence of a digital bloodhound. The formal designation follows an astronomical convention, the year, the half-month of a discovery, and a sequence number that marks it as the first such object that was found in that particular 2-week window. But the names matter less than what this thing represents: a messenger from somewhere else entirely. The discovery came during the routine observations, the kind of a methodical sky patrol that happens every clear night around the world. The Atlas, with its 4 wide-field telescopes, photographs the entire visible sky every 2 days, comparing each image against the previous ones, looking for anything that moves. Most of the time, they find the asteroids, the chunks of a rock that are orbiting our sun in the predictable patterns. Sometimes they find the comets, the dirty snowballs that are following the elliptical paths that carry them from the outer reaches of our solar system to the inner warmth, and then back again. But on that July night, something different appeared in the data: an object that was moving too fast in the wrong direction on a trajectory that broke all of the rules. You see, everything in our solar system is gravitationally bound to the sun. The asteroids and the comets might swing out to the incredible distances, but they are still the prisoners of our star's gravity well. Their orbits are the ellipses, the closed curves that bring them back again and again, sometimes over the millions of the years, but always and eventually a returning home. This thing was different. Its path through a space was hyperbolic, an open curve that would carry it through our solar system exactly once, never to return. It was moving roughly 19 kilometers per second relative to our sun, which was fast enough to escape our gravitational embrace entirely. That speed, that trajectory could only mean one thing. It came from an interstellar space, and it is heading back there. Think of it as a cosmic highway traveler that is briefly exiting at our solar system for a fuel and a snack before emerging back onto the interstellar interstate, except that this traveler has been on the road for the millions, possibly the billions of the years. The mathematics of its journey are staggering. Based on its current trajectory, we can backtrack its path through the galaxy. This wanderer likely originated from the direction of the constellation of Lynx, though pinpointing its exact stellar neighborhood is impossible after so much of a time and a distance. It may have been ejected from its birth system by the gravitational interactions with the giant planets, or perhaps its parent star went through the death throes that sent the chunks of itself spinning into the void. Either way, it has been traveling through the space that is between the stars longer than a complex life has existed on the Earth. As an October approaches, a 3I-ATLAS is heading toward its closest approach to our sun, what the astronomers call a perihelion. On an October 29th or a 30th, depending on the precise timing calculations, it will reach its minimum distance of about 1.4 astronomical units from our star. That is roughly 210 million kilometers, which is comfortably outside the Earth's orbit, but close enough to feel the sun's warmth and to begin the ancient dance of an ice that is turning to a gas. For the Earth, the encounter is even more distant. Our visitor will pass no closer than 1.8 astronomical units from our world, about 270 million kilometers, or roughly 170 million miles. That is nearly twice the distance that is between the Earth and the Sun. There is no cause for an alarm and no reason to cancel the weekend plans. This is an astronomy, not an Armageddon. But here is what makes a 3I-ATLAS special. Unlike its famous predecessor, an Oumuamua, which remained frustratingly inert and asteroid-like throughout its visit, this newcomer is putting on a show. It has developed what the astronomers call a coma, a cloud of a gas and a dust that is surrounding its nucleus, along with the beginnings of a tail. It is a classic comet behavior, the kind of an activity that happens when an ancient ice is warmed in the sun's radiation and begins to sublimate directly from a solid to a gas. The ATLAS survey, which discovered our visitor, represents a revolution in how we watch the sky. The 4 telescopes in Hawaii, a South Africa, a Chile, and another in Hawaii work together as a global network, each one of them equipped with the cameras that are capable of imaging the enormous sections of a sky in a single exposure. They are not looking for a beauty, they are looking for a change. Anything that moves, anything that brightens, and anything that appears where a nothing was before gets flagged for a follow-up observation. It is this kind of a systematic robotic vigilance that has changed our odds of catching the interstellar visitors. Before the automated surveys, we might have missed a 3I-ATLAS entirely or noticed it too late to gather a meaningful data. Now we can track these cosmic wanderers from the moment that they become bright enough to detect until they fade back into the interstellar darkness. But as our instruments have grown more sophisticated, so have the mysteries that they reveal. Because while a 3I-ATLAS might look like a comet, it is beginning to behave in the ways that make the astronomers reach for their calculators with the unusually furrowed brows. The universe, it seems, still has the surprises to share. A growing mystery. When the Hubble Space Telescope turned its sharp eye toward a 3I-ATLAS in an early autumn, the images that it sent back were both beautiful and puzzling. Our interstellar visitor appeared as a teardrop-shaped cocoon of a dust which was glowing faintly in a reflected sunlight. The physics seemed to be straightforward enough. A solar radiation was pushing the tiny particles away from the nucleus, creating the classic comet tail that always points away from the sun, regardless of the object's direction of travel. It was a textbook comet behavior, except that the textbook was written for the objects that were born in our own solar system. The first hint that something unusual was happening came from the size estimates. Measuring the actual nucleus of a comet, the dirty snowball at its heart, is notoriously difficult when it is surrounded by a bright, expanding cloud of a gas and a dust. It is like trying to estimate the size of a light bulb when you are staring directly into its glare. The current calculations suggest that the solid core of a 3I-ATLAS spans somewhere between 320 meters and 5.6 kilometers across. That is a range that is wide enough to drive the several space shuttles through sideways. The uncertainty exists because the growing coma increasingly hides the nucleus from a view like a fog that is obscuring a distant building. What we can see is the cloud. What we are trying to measure is the source. But it was the James Webb Space Telescope that revealed the first truly strange detail. The JWST, with its infrared vision, can peer through the dust clouds and analyze the chemical composition of the gases that are streaming away from the nucleus. What it found was unexpected, an unusually high ratio of a carbon dioxide to a water vapor, about 8 parts of a carbon dioxide to every 1 part of a water. Now you might think, so what? It is a different mix of the ingredients. But in the world of cometary science, the ratios like this are nearly unprecedented. Most of the comets that we have studied, including the previous interstellar visitor, A2 Borisov, show much more water relative to a carbon dioxide. A water ice is common throughout the outer reaches of the planetary systems, where the temperatures drop low enough for a water to freeze a solid. A carbon dioxide, however, freezes at the even lower temperatures. To end up with such a carbon dioxide-rich composition, a 3I-ATLAS would have had to form in an extremely cold environment, or perhaps has suffered some kind of an intensive radiation exposure that preferentially removed its water ice over the millions of the years of an interstellar travel. The plot thickened in late August when the ground-based telescopes began to detect a hydrogen cyanide, or an HCN, in the comet's growing atmosphere. Now, before you start worrying about the cosmic poison clouds, remember that we are talking about the incredibly tiny amounts of a gas that are spread across the millions of the cubic kilometers of a space. The detection required a sophisticated spectroscopy to identify the characteristic signature of the cyanide molecules that were fluorescing in a sunlight. What made this interesting was not the presence of a cyanide. Many of the comets produce an HCN as they warm up, but the timing. The gas appeared gradually, a strengthening over the several weeks as the comet drew closer to the sun. It suggested that the different types of an ice were sublimating at the different temperatures, like the layers of an onion that were peeling away as our visitor entered the warmer regions of a space. By an early September, something even more intriguing emerged: the hints of a greenish tint in some of the images of the comet's coma. The green comets are not entirely unusual. The color often comes from the diatomic carbon molecules, or a C2, or sometimes from the same cyanide that we had already detected. But the specific source of a 3I-ATLAS's green glow remained frustratingly unclear. A definitive spectroscopic confirmation of a diatomic carbon would have to wait for the more detailed observations. Meanwhile, a team of the researchers submitted a preprint, an early research paper which was not yet peer-reviewed, that was describing the unusual polarization properties in a light that was reflecting from the comet's dust cloud. A polarization is a measure of how the light waves are oriented, and it can tell us about the size, the shape, and the composition of the dust particles. The preliminary results suggested something odd about the dust grains that were surrounding a 3I-ATLAS, though and exactly what remained unclear. Here is where we need to pump the brakes on a speculation. The preprints are the academic equivalent of the early drafts, which are important for sharing the rapid results, but are not yet vetted by the rigorous process of a peer review. They represent the hypotheses and the preliminary data, not the established facts. The polarization results, while they were intriguing, needed a confirmation and a careful analysis before drawing the firm conclusions. What we definitely were not seeing were the kinds of the signals that would suggest an artificial origin. There were no narrowband radio transmissions, no laser communications, and no impossible maneuvers that would require the rocket engines. The comet was following a perfectly natural trajectory that was dictated by a gravity and the gentle pressure of a solar radiation on its dust cloud. The scientists at the NASA and elsewhere were quick to caution against leaping to the extraordinary conclusions. Yes, a 3I-ATLAS showed some of the unusual characteristics. Yes, it was behaving differently from the solar system comets that we had studied before. But an unusual and an artificial are separated by a chasm of an evidence that had not been bridged. The tendency to see the patterns where none exist is a fundamental feature of a human cognition, where the pattern-matching creatures evolved to spot the tiger in the tall grass, even when it might just be the shadows and a wishful thinking. In an astronomy, this instinct serves us well when identifying the genuine phenomena, but it can also lead us astray when dealing with limited data and our own desire for a cosmic significance. Still, there is something deliciously mysterious about an object that travels between the stars, carrying a chemistry that is unlike anything in our local neighborhood. Even if a 3I-ATLAS turns out to be entirely natural, which remains the most likely explanation, it represents a sample of the materials from somewhere else entirely, a messenger that is carrying the news of the conditions in the stellar nurseries that we will never visit around the stars, that we can barely see. But what if, just for the sake of an argument, we wanted to imagine something more deliberate behind its journey? What signs would we look for? What evidence would convince us that we were dealing with an intelligence rather than an ice? Signs of an intelligence. If you were an alien intelligence that was planning to study a solar system that was undetected, how would you do it? The obvious answer, and the one that is favored by a science fiction, would be to build a massive mothership that was bristling with the sensors and to park it in an orbit around the target planet. But that approach has a fatal flaw. It is rather hard to miss. A more subtle strategy might involve what the researchers call the lurker probes, the artificial objects that were designed to blend in with the natural phenomena. They would be patient, quiet, and clever enough to masquerade as something that was ordinary, like perhaps a comet. This is a pure speculation, of course, but it is not an entirely unscientific speculation. The search for the technosignatures and evidence of an alien technology has become a legitimate field of an astronomical research, and the interstellar objects, which are rare and exotic, represent the natural candidates for a closer scrutiny. So what would we look for in a genuine artificial visitor? First, the anomalous accelerations. Any object that is moving through a space is subject to the predictable forces, a gravity from the sun and the planets, plus the gentle radiation pressure that pushes on a dust and a gas. If something were changing a course without an obvious physical cause, a speeding up, a slowing down, or a changing a direction in the ways that could not be explained by the natural forces that would raise the serious questions. The previous interstellar visitor, an Oumuamua, actually showed exactly this kind of a behavior. As it flew past the sun in 2017, it accelerated slightly in a direction that could not be entirely explained by a gravity alone. The effect was small but immeasurable, and it sparked the years of a scientific debate. The natural explanations exist in outgassing from the hidden ice deposits, or even the possibility that an Oumuamua was a fragment of a solid hydrogen. But a consensus remains elusive. Second, the coordinated maneuvers. If an object were making the purposeful changes to its trajectory, especially in a response to the planetary positions or a solar activity, that would be difficult to explain naturally. The comets can show the sudden changes in a brightness or a gas production as the different types of an ice are exposed to a sunlight, but the controlled course corrections would be another matter entirely. Third, the structured emissions. Any advanced probe would presumably need to communicate with its builders, either to send back a data or to receive the new instructions. We would expect to see the narrowband radio signals, the laser communications, or other forms of an artificial transmission. These would stand out against the broadband background of a natural cosmic noise like a violin solo in a thunderstorm. Fourth, the thermal anomalies. The powered equipment generates a waste heat even in the cold of a space. If something were running the active sensors, the computers, or the communication systems, it would glow faintly in the infrared wavelengths. The space telescopes that were equipped with a thermal imaging could potentially detect the artificial heat sources against the cold background of a space. So far, a 3I-ATLAS has shown none of these smoking gun indicators. Its trajectory follows the laws of a celestial mechanics with a boring predictability. No radio telescopes have detected the artificial signals, and no thermal cameras have spotted the mysterious heat sources. If this is a probe, it is either a powered down and extraordinarily well disguised, or an operating in the ways that we have not thought to monitor. But that does not stop us from examining the unusual features that it does display. The polarization measurements, which are still awaiting a peer review, suggest something odd about the dust particles in its coma. The chemical composition that is dominated by a carbon dioxide differs significantly from the typical solar system comets. Even the apparent sunward glow, a brightness on the side that is facing our star, could be interpreted as an evidence of the active processes rather than a simple thermal heating. Of course, each of these features has the potential natural explanations. A polarization depends on a dust, a grain size, and a composition which could vary dramatically between the different stellar nurseries. The chemical ratios reflect the formation conditions and the long journey through an interstellar space. A sunward brightness can result from the complex gas and a dust dynamics as a comet approaches a perihelion. The NASA scientists have been admirably careful to emphasize these natural alternatives. In a field where an extraordinary claim requires an extraordinary evidence, their role is to counsel a patience and a skepticism. The history of an astronomy is littered with the initially mysterious phenomena that yielded to the mundane explanations once a better data became available. But here is the fascinating thing about a technosignature research. Even the negative results teach us something that is valuable. Every natural explanation that we confirm, every ordinary comet that we identify, helps us to understand what the genuine anomalies would look like. We are building a baseline of a normal behavior against which the truly unusual objects would stand out like the cosmic sore thumbs. Borisov, the previous interstellar comet, provided exactly this kind of a control case. It behaved like a perfectly ordinary comet throughout its visit, a standard chemical composition, a predictable brightening, and a normal dust production. If all of the interstellar visitors are the variations on the same natural theme, then the genuinely artificial objects should be recognizably different. Of course, there is another possibility that we have not considered yet. What if an intelligence does not look like what we expect? What if the signs that we are searching for, the radio signals, the heat sources, and the controlled maneuvers represent our own technological biases rather than the universal features of the advanced civilizations? Maybe the universe is full of the patient watchers who learned a long time ago that the best observation posts are the ones that nobody notices. Maybe they have been drifting between the stars for the millions of the years, collecting data on the young civilizations like ourselves, waiting for the right moment to say hello. Or maybe, just maybe, they are already saying hello, and we have not figured out how to listen. The first suspicion watching us. Imagine that you are walking through an African game preserve and you notice something odd. The animals seem to be unusually calm, the predators ignore a prey, and the territorial disputes are minimal. Everything appears to be almost managed. You might begin to suspect that this is not truly a wild nature, but rather a carefully maintained environment where some unseen intelligence has established the rules to keep the peace. Welcome to the Zoo Hypothesis, one of the more intriguing attempts to explain why the universe seems so quiet despite its obvious potential for a life. The idea, which was first proposed in 1973 by the MIT radio astronomer John Ball, suggests that the advanced alien civilizations might operate under a galactic version of the Prime Directive. Just as we try to minimize our impact on the wildlife preserves and the indigenous cultures, perhaps the spacefaring species have agreed to leave the developing civilizations alone. We are not being ignored, we are being protected. Under this scenario, the Earth exists in a kind of a cosmic nature preserve. We are free to evolve, to develop our own technology, and to make our own mistakes without an interference from the older, wiser civilizations. They watch from a respectful distance, taking the notes, perhaps, and occasionally, placing the subtle limits on our expansion, but never directly intervening. It is an appealing idea, especially when you consider the alternative possibilities. If the galaxy were truly a wild, free-for-all of the competing civilizations, then the younger species like ourselves might not survive their first contact with the more advanced neighbors. The zoo model suggests a universe that is governed by an ethics and a restraint, where a power comes with a responsibility. But how would such a system work in a practice? How do you monitor a civilization without being detected? One of the possibilities involves what the researchers call the lurker probes, the artificial objects that are placed in the strategic locations to observe and to report back to their builders. These would not need to be the massive constructions that were bristling with the obvious technology. The most effective surveillance satellite would be the one that looked completely natural, something that was small, patient, and clever enough to masquerade as a space debris, an asteroid, or, well, a comet. Now, before we start fitting a 3I-ATLAS for a tinfoil hat, let's be clear. There is no credible evidence that our interstellar visitor is anything other than a natural object. But the zoo hypothesis does provide an interesting lens through which to examine the broader question of a cosmic silence. If the advanced civilizations are out there but are staying hidden, then the occasional visitors from a deep space might be our only glimpses of the larger galactic community. The beauty of using the interstellar objects as a camouflage is that they are naturally rare and exotic. Before the automated sky surveys like the Atlas, we might have missed them entirely. Even now, with our best detection systems, we have confirmed only the 3 interstellar visitors in the 8 years. A civilization that was wanting to place the long-term observers in our solar system could hardly ask for a better cover. Consider the operational advantages. An artificial probe that was disguised as a comet could drift through a space for the millions of the years without raising a suspicion. It could approach relatively close to the inner planets during the perihelion passages, gathering the high-resolution data on an atmospheric composition, an industrial emission, and the signs of a technological development. If it was questioned, it would appear to be exactly what it seemed, a chunk of an ice and a rock that was following a natural orbital mechanics. The timing of a 3I-ATLAS's arrival is, from this perspective, intriguing. We are living through what might be called a humanity's great broadcasting period, the era when our radio and a television signal first began to leak into a space at the detectable levels. We have also recently entered the space age, developed the nuclear weapons, and begun the serious discussions about an interstellar travel. If you were monitoring a developing civilization, now might be an excellent time to take a closer look. But let's inject some of a healthy skepticism into this speculation. The Vera Rubin Observatory, which is currently under a construction in Chile, will soon begin the Legacy Survey of Space and Time, a decade-long project that will photograph the entire southern sky every few nights. The current estimates suggest that the LSST could detect the dozens or even the hundreds of the interstellar objects per year once it reaches a full operation. If most of these turn out to be the natural comets and the asteroids, then a 3I-ATLAS becomes considerably less special, just one sample from the ongoing exchange of a material between the stellar systems. The galaxy is probably full of the ejected planetesimals that are drifting between the stars, and we are only now developing the instruments that are sensitive enough to spot them regularly. The zoo hypothesis also faces a more fundamental challenge, the problem of a consensus. For such a system to work, all of the spacefaring civilizations would need to agree to the same ethical framework. A single aggressive species, the galactic equivalent of the poachers, could disrupt the entire preserve. The fact that we have not been contacted or conquered might simply mean that the aggressive species are rare, not that the protective species are common. Still, there is something almost comforting about the zoo model. It suggests that we are not alone, but it also implies that we are safe. Our cosmic neighbors in this scenario are the patient gardeners rather than the hungry predators. They are watching our development with the same mixture of a concern and a fascination that we feel when observing a nest of the baby birds. Of course, there is a darker interpretation of a cosmic silence. What if the civilizations stay quiet, not out of a benevolence, but out of a fear? What if the universe operates under the harsher rules, where broadcasting your location is equivalent to a painting a target on your world? This brings us to another possibility entirely, one that views an interstellar space not as a peaceful preserve, but as a hunting ground where only the silent survive. But that is a story for the next chapter of our journey. For now, as a 3I-ATLAS continues its quiet passage through our solar system, we are left with the questions rather than the answers. Are we witnessing the arrival of a natural visitor that is carrying the samples from the alien worlds? Or are we being studied by an intelligence that is so subtle that we cannot quite convince ourselves that it exists? The universe, it seems, prefers to keep its secrets, at least for now. The Great Silence explained. Let's step back from our mysterious visitor for a moment and consider the bigger picture. The Fermi Paradox is not just about one unusual comet. It is about the profound disconnect between what we would expect from a galaxy that is teeming with a life and what we actually observe, nothing but a cosmic silence. The numbers really are staggering when you sit down and work through them. The conservative estimates suggest that our galaxy contains at least 100 billion stars. Many of these are similar to our sun, burning steadily for the billions of the years. The recent discoveries by the Kepler Space Telescope and other planet-hunting missions suggest that roughly 1 in 5 sun-like stars hosts an Earth-sized planet in its habitable zone, that sweet spot where a liquid water can exist on the surface. Do the math, and you get roughly 10 billion potentially habitable worlds in our galaxy alone. Even if a life is extraordinarily rare and arising on just one planet in a million, we should still have 10,000 civilizations in our cosmic neighborhood. But here is the kicker. Our galaxy is over 13 billion years old. A star formation began early in its history, which means that some of the stellar systems have had a several billion-year head start on us. If an intelligent life developed elsewhere, even just 1% earlier than it did on the Earth, those civilizations would have had the tens of the millions of the additional years to develop a technology, to explore space, and to leave the detectable traces of their existence. With that much of a time and that many of the potential starting points, the galaxy should be thoroughly explored by now. We should see the signs of the megastructures around the distant stars, catch the radio leakage from the alien broadcasts, or at a minimum detect the infrared waste heat from the advanced civilizations that are consuming their star's energy output. Instead, we find a silence. This cosmic quiet has spawned the dozens of the proposed solutions, but most of them fall into a few broad categories. Let's examine them like a detective that is reviewing the case files, each one of them offering a different answer to the central mystery. The rare Earth hypothesis suggests that we are the winners of an incredibly unlikely lottery. Yes, the planets are common, but the Earth-like planets with the stable climates, the protective magnetic fields, the large moons, and the Jupiter-sized outer planets that are acting as the cosmic vacuum cleaners might be extraordinarily rare. Add in the need for a plate tectonics, the right atmospheric composition, and a host of the other factors, and perhaps we are not just rare, we are unique. This solution has the advantage of requiring no assumptions about an alien behavior or a galactic politics. It simply proposes that the universe is harder to live in than we assumed. But it also implies a rather lonely cosmos, where a consciousness might arise only once per galaxy, if at all. The Great Filter represents a more troubling possibility. Maybe an intelligence is not rare, but a longevity is. Perhaps there is some universal stumbling block that claims the civilizations shortly after they reach a technological adolescence. The nuclear weapons, a climate change, an artificial intelligence, or a biotechnology that has gone wrong, some challenge that is simply too difficult for the young civilizations to navigate. The terrifying version of this idea is that the filter lies ahead of us rather than behind us. Maybe developing the spaceflight capabilities invariably leads to a self-destruction. Maybe every civilization that reaches our current level of a technological development has only the decades or the centuries left before something goes catastrophically wrong. But there are the more optimistic interpretations of a cosmic silence. Perhaps the advanced civilizations simply have the better things to do than to broadcast their presence to the universe. Once you have solved the basic problems of an energy, a resource, and a mortality, you might turn inward and exploring the virtual realities and enhancing a consciousness or pursuing the forms of an art and a philosophy that make an interstellar communication seem primitive and pointless. This leads us to what we might call the transcendence hypothesis, the idea that the sufficiently advanced civilizations graduate to the forms of an existence that we would not recognize as a technological. They become something like the cosmic hermits, so focused on an internal development that an external universe becomes irrelevant. From our perspective, such civilizations would be effectively invisible. They would use the minimal physical resources, produce no detectable waste products, and show no interest in an expansion or a communication. They might exist all around us in the virtual realities, the alternate dimensions, or the states of a being that our science cannot yet detect or comprehend. Alternatively, maybe they are out there but are staying deliberately quiet. The zoo hypothesis suggests a benevolent supervision, the older civilizations that are maintaining a hands-off policy toward the younger species like ourselves. It is comforting to imagine the wise, patient gardeners that are tending to the galaxy's development, but it requires a remarkable restraint and a consensus among the species that might have the very different values and the motivations. The dark forest hypothesis offers a grimmer take on a deliberate silence. It was proposed by the Chinese science fiction author Liu Cixin, and it suggests that the universe operates under the logic of a dark forest, where revealing your location brings a swift destruction from the competitors. Every civilization faces a terrible choice: a remain hidden and a survive, or a broadcast your presence, and a risk an annihilation by someone who is more powerful. Under this model, the galaxy could be full of the civilizations, all of them hiding in a fearful silence, which are afraid to make the first move that might expose them to the cosmic predators. It is a paranoid universe where a first contact means a first strike capability. Then there are the technical solutions, the possibilities that focus on how we are searching rather than what we might find. Maybe the alien communications use the technologies that we have not invented yet, a quantum entanglement, the gravitational waves, or the forms of a physics that we do not yet understand. We are like someone who is trying to detect the cell phone conversations by using a telegraph key, looking for the right thing in the wrong way. Or perhaps the signals are there, but they are brief directional, or encoded in the ways that make them nearly impossible to distinguish from the natural phenomena. A truly advanced civilization might use the communication methods that are so efficient that their signals would be invisible to anyone who is lacking the proper decoding algorithms. This is where our interstellar visitors become particularly interesting. Even if they are entirely natural, the comets like a 3I-ATLAS represent a form of a cosmic communication, not the intentional messages, but the samples of a chemistry and a physics from the other stellar systems. They are the letters in the bottles that are carrying an information about the conditions around the distant stars and the processes that shape a planetary formation. By studying the compositions, the sizes, and the behaviors of the interstellar objects, we are essentially conducting a form of an archaeology and examining the debris that was left behind by the solar system formation processes throughout our galactic neighborhood. Each visitor tells us something about the materials that are available for a planet formation, the dynamics of a stellar evolution, and the kinds of the environments where a life might or might not take a hold. In this sense, a 3I-ATLAS does not need to be an artificial to be significant. Whether it is a natural comet or something that is more exotic, it represents our most direct sampling of the conditions that are beyond our solar system. It is a messenger from the cosmic deep, carrying the news of the worlds that we may never visit. But as we will see next, this visitor is not our first interstellar guest, and the stories that were told by its predecessors are equally fascinating, if in the very different ways. The historical echoes of the visitors. To understand what makes a 3I-ATLAS special, we need to meet its predecessors, the only other confirmed visitors from beyond our solar system. Each one of them tells a different story about the space that is between the stars, and together, they are a beginning to sketch the first crude portrait of our galactic neighborhood. The first interstellar object that was ever confirmed, a 1 Oumuamua, arrived like a cosmic mystery novel that was discovered on an October 19, 2017 by the Pan-STARRS telescope in Hawaii. It initially appeared to be an asteroid, a bare rock that was tumbling through a space without the gas, and a dust coma that was typical of the comets. But an Oumuamua was strange from the start. Its shape was utterly unlike anything that we had seen in our solar system, and extremely elongated, perhaps 10 times longer than it was wide, like a cosmic cigar or a pancake that was spinning end over end. Its surface was surprisingly reflective, almost metallic in an appearance, and it showed the dramatic variations in a brightness as it rotated, which was suggesting either an extremely elongated shape or the unusual surface properties. A more puzzling still was its motion. As an Oumuamua swung around the sun and headed back toward an interstellar space, it accelerated slightly in a direction that could not be entirely explained by the gravitational forces alone. The effect was small, but immeasurable about what you would expect from a gentle rocket push or from a gas that was jetting off a comet's surface. The problem was that nobody could see any gas. This non-gravitational acceleration sparked the years of a scientific debate and the increasingly exotic explanations. Maybe an Oumuamua was venting a hydrogen gas that was invisible to our instruments. Maybe it was a fragment of a hydrogen iceberg that was slowly sublimating in the sun's heat. Some of the researchers even suggested that it might be an artificial light sail that was pushed by a solar radiation pressure, though this idea required an Oumuamua to be an extraordinarily thin and lightweight. The controversy highlighted a fundamental challenge in studying the interstellar objects. They do not stick around. By the time that we realize what we are looking at, they are already on their way out of the solar system, moving too fast and getting too faint for the detailed follow-up observations. An Oumuamua became invisible to the ground-based telescopes within the months of its discovery, leaving behind more questions than the answers. The second confirmed interstellar visitor could not have been more different. A 2 Borisov, which was discovered on August 30, 2019 by the amateur astronomer Gennady Borisov by using a homemade telescope in the Crimea, behaved exactly like what the astronomers expected an interstellar comet to be. From the moment of its discovery, a Borisov displayed a classic coma and a tail. As it approached the sun, it brightened predictably, developed an increasingly prominent dust trail, and showed all of the chemical signatures of a typical comet: a water vapor, a carbon monoxide, and the dust particles creating a glowing envelope around its nucleus. A spectroscopic analysis revealed a refreshingly familiar composition. The ratio of a water to a carbon monoxide in a Borisov's coma matched the values that were seen in many of the solar system comets. Its dust properties, its grain sizes, and its gas production rates all fell within the range of a normal cometary behavior. Even its nuclear size, which was estimated at between 100 meters and a few kilometers across, was perfectly ordinary. In a scientific term, a Borisov was almost a boring, and that was wonderful. You see, a Borisov provided something that was invaluable, a control case. It showed us what a normal interstellar comet looks like and establishing a baseline against which the future visitors could be compared. If all of the interstellar objects were as mysterious as an Oumuamua, we might start to suspect that the space that is between the stars operated under the different physical laws. A Borisov proved that at least some of the interstellar wanderers are exactly what they appear to be, the chunks of an ice and a rock that are following a predictable physics. The comet's origin story was equally straightforward. Backtracking its trajectory through a space, the astronomers determined that a Borisov likely came from the direction of the constellation of Cassiopeia, possibly ejected from its birth system by the gravitational interactions with the giant planets. It had been traveling through an interstellar space for the millions of the years before entering our solar system, carrying with it the samples of the materials from its distant homeland. During its closest approach to the Sun in December 2019, the multiple space telescopes trained their instruments on this cosmic visitor. The Hubble captured the detailed images of its nucleus and its coma structure. The ground-based observatories measured its chemical composition and its dust properties, and the European Southern Observatory's Very Large Telescope tracked the changes in its brightness and its activity levels. The data confirmed what an initial observation suggested. A 2 Borisov was remarkably similar to the comets that were born in our own solar system despite traveling from an entirely different stellar neighborhood. This similarity suggested that the basic processes of a planet formation, the condensation of an ice and a dust in the cold outer regions of the stellar systems might be remarkably universal, but the discovery also raised the intriguing questions about a galactic chemistry. If the comets from the different star systems show the similar compositions, then what does that tell us about the materials that are available for a planet formation throughout our region of the galaxy? Are the building blocks of a life, water, the carbon compounds, and the organic molecules distributed fairly uniformly among the stellar systems? Or was a Borisov's apparent familiarity misleading, masking the subtle differences that could reveal the important details about its origin? These questions became more pressing with the arrival of our third confirmed visitor, a 3I-ATLAS. As we have seen, it displays a comet-like activity that is similar to a Borisov, but with a chemical composition that is distinctly different from either the typical solar system comets or its immediate predecessor. The pattern that is emerging from our small sample of the interstellar visitors is intriguing, one that is mysterious and inactive. 1 Oumuamua, one that is familiar and well-behaved, 2 Borisov, and now one that is active but chemically unusual, 3I-ATLAS. It is like a meeting the 3 strangers from the same distant city and a finding that each one of them has a completely different personality. The rarity of these encounters makes each one precious. In the 8 years since an Oumuamua's discovery, we have confirmed only the 3 interstellar objects despite the increasingly sophisticated sky surveys. The Vera Rubin Observatory, when it begins its operations, is expected to find the dozens per year, transforming the interstellar visitors from the rare curiosities into a regular part of an astronomical research. But for now, we are still in the early days of an interstellar archaeology. Each visitor provides a unique sample of the conditions elsewhere in the galaxy, a snapshot of a chemistry and a physics from the stellar systems that we may never be able to visit directly. They are like the core samples from the cosmic deep, carrying an information about a planet formation, a stellar evolution, and the distribution of the materials throughout our galactic neighborhood. The controversy that was surrounding an Oumuamua also taught us the important lessons about the scientific process. An initial mystery does not necessarily imply the exotic explanations. A better data and the more sophisticated models often resolve the apparent anomalies without requiring the revolutionary new physics or, for that matter, the alien artifacts. As we have refined our understanding of how the objects behave in the outer solar system, we have developed the better tools for distinguishing between the genuinely unusual phenomena and the normal complexity of a celestial mechanics. The non-gravitational accelerations used, for an instance, can result from the several natural processes, an asymmetric outgassing that changes in a shape due to a sublimation, or even the gradual loss of a surface material under a solar heating. This improved understanding makes the features of a 3I-ATLAS more interesting, not less. Its unusual chemical composition cannot be easily dismissed as an observational artifact or a modeling error. The high ratio of a carbon dioxide to a water vapor represents a genuine difference from both the solar system comets and A2 Borisov. Whether this difference reflects the formation conditions in its birth system, the modifications during its long journey through an interstellar space, or something else entirely, remains an open question. But it is exactly this kind of a question that makes the interstellar visitors so valuable for an astronomy. They provide the natural experiments in a comparative planetology and allowing us to study the results of the planet formation processes under the different conditions and in the different environments. And occasionally, they force us to confront the more speculative possibilities. If an intelligence were watching our solar system, how would it do so without being detected? The evidence of the watcher. Let's examine the evidence that is surrounding a 3I-ATLAS with the methodical care of the investigators who are processing a crime scene. Not because we suspect a criminal activity, but because an extraordinary claim requires an extraordinary scrutiny. And some of the claims that are swirling around our interstellar visitor have been quite extraordinary indeed. First, the polarization measurements. A team of the researchers published the preliminary results that were suggesting that a light that was reflected from a 3I-ATLAS's dust cloud shows the unusual polarization properties. A polarization is essentially a measure of how the light waves are oriented, whether they vibrate in the random directions or show a preferential alignment. For most of the comets, the polarization measurements help us to understand the size, the shape, and the composition of the dust particles in the coma. The preliminary data suggested a negative polarization at the certain viewing angles, which is uncommon but not unprecedented in the solar system objects. What made it interesting was how different the pattern appeared compared to the typical comets. However, and this is crucial, these results were published as a preprint, which means that they have not yet undergone the rigorous peer review process that validates the scientific findings. The preprints serve an important function in an astronomy and allowing a rapid sharing of the time-sensitive observations, but they are also preliminary by a definition, which are subject to a revision, a correction, or even a retraction as more data becomes available. The polarization measurements of a 3I-ATLAS remain intriguing, but they are unconfirmed. Meanwhile, the Hubble's sharp vision revealed the comet's morphology in an exquisite detail. The images showed a classic teardrop-shaped dust envelope with a material that was being swept away from the nucleus by a solar radiation pressure. The symmetry and the behavior of this dust cloud followed exactly the patterns that were predicted by a standard comet. Physics, a solar heating, vaporizes an ice. A gas drags the dust particles along, and a radiation pressure pushes the debris into a tail that is pointing away from the sun. Nothing about the structure suggested an artificial origin or the control processes. It looked quite simply like a comet that was doing the comet things. The James Webb Space Telescope provided perhaps the most significant findings. The JWST's infrared spectroscopy revealed that unusual chemical composition that we discussed earlier, a carbon dioxide to a water vapor ratio of roughly 8:1, which was among the highest ratios that were ever measured in any comet. The additional gases that were detected included a carbon monoxide, a carbonyl sulfide, and the various organic compounds, which were painting a picture of an object that was rich in the carbon-bearing molecules. This chemistry tells a story about the formation conditions. A water ice condenses at the higher temperatures than a carbon dioxide ice, so a carbon dioxide-rich composition suggests a formation in an extremely cold environment, or perhaps a selective loss of a water during the long journey through an interstellar space. Neither scenario requires an intelligence, just an unusual physics or a chemistry. The ground-based telescopes added their own pieces to the puzzle. A detection of a hydrogen cyanide began in late August, with the production rates that were increasing as the comet approached the sun. The timing made perfect sense. The different types of an ice sublimate at the different temperatures, so we would expect to see the various gases that were appearing in a sequence as a solar heating penetrated deeper into the nucleus. By an early September, some of the images began to show the hints of a greenish coloration in the comet's coma. The green comets are not unusual. The color typically comes from the diatomic carbon molecules or the cyanide fluorescing. But a definitive identification of the specific molecules that were responsible required the more detailed spectroscopy than was initially available. The size estimates remained frustratingly uncertain. The growing coma increasingly obscured the nucleus, which was making it difficult to determine whether we were looking at a large object with a low activity or a small object that was punching above its weight. The current estimates place the nucleus diameter somewhere between 320 meters and 5.6 kilometers, a range that encompasses everything from a city block to a small mountain. Now here's where we need to address some of the more sensational claims that appeared in a media coverage. The various outlets suggested that a 3I-ATLAS was half the size of the Sun, or showed the other impossible characteristics. These claims appear to have confused the size of the comet's expanding coma, which can indeed grow to the enormous dimensions with the size of the solid nucleus at its center. The coma is mostly an empty space with the tiny dust particles that are scattered throughout. A saying that it is huge is like claiming that a fog is a solid because you can see it from the miles away. The actual comet, the rocky icy nucleus, remains quite small by an astronomical standard. Similarly, some of the reports describe the mysterious sunward glows or the anytail features as an evidence of an artificial propulsion or the controlled emissions. In a reality, these phenomena can result from the natural dust dynamics. The particles of the different sizes are pushed by a solar radiation at the different rates, creating the complex structures that can appear to point in the unexpected directions depending on a viewing angle and a timing. The NASA scientists were admirably clear in their public statements. Based on current evidence, a 3I-ATLAS appears to be a natural comet that is following a predictable physics. While they acknowledged its unusual characteristics, particularly the chemistry, they found no credible evidence of an artificial origin or a controlled behavior. This brings us to a crucial point about the search for the technosignatures. If an advanced civilization were operating the stealth probes in our solar system, what would we expect to detect? Most likely some form of an artificial signal. The narrowband radio transmissions, the laser communications, or the modulated light curves that could not be explained by the natural processes. We might also expect the thermal signatures from the powered equipment, the unusual accelerations from the propulsion systems, or the coordinated maneuvers in a response to the planetary positions or a solar activity. An advanced material might show the spectroscopic signatures that were unlike anything in a natural mineralogy. None of these smoking guns have been detected around a 3I-ATLAS. The radio telescopes that are monitoring the object have found no artificial transmissions. The infrared observations show a thermal emission that is consistent with a solar heating of the natural materials, and the comet's trajectory follows the laws of a celestial mechanics without requiring a thrust or the course corrections. If this is a probe, it is either completely powered down and operating in the ways that we have not thought to monitor, or using a technology that is so advanced that it is indistinguishable from the natural phenomena. Any of these possibilities would make a detection extraordinarily difficult with the current instruments. But perhaps we are asking the wrong question. Instead of looking for the obvious signs of an intelligence, maybe we should consider the more subtle possibilities. What if the advanced civilizations have learned that the best surveillance is the kind that looks entirely natural? What if a patience, rather than a technology, is the mark of a true cosmic sophistication? Why remain silent? If an intelligence exists elsewhere in the galaxy, and the math suggests that it almost certainly does, then why have not we heard from anyone? The question assumes that the advanced civilizations would want to communicate, but perhaps that assumption reveals more about a human nature than a cosmic reality. Consider what we know about an intelligence here on the Earth. The most successful species are not necessarily the loudest ones. The humans dominated the planet not through a roaring and a chest beating, but through a cooperation, a planning, and the patient accumulation of a knowledge. Maybe a cosmic intelligence follows the similar patterns, favoring a subtlety over a spectacle. The zoo hypothesis, which we touched on earlier, suggests that the advanced civilizations operate under a kind of a galactic prime directive, a commitment to a non-interference with the developing worlds. Under this model, we are living in a carefully maintained preserve, which is studied but not contacted, and which is protected but not controlled. The logic is compelling from an ethical standpoint. If you are the thousands or the millions of the years more advanced than a developing civilization, a direct contact would be inherently disruptive. Your mere presence would alter their natural development, potentially stunting their growth, or creating a harmful dependency. A better to watch from a distance, letting them to find their own path to a cosmic citizenship. This approach would require a remarkable patience and a coordination among the spacefaring species. Every advanced civilization in our galactic neighborhood would need to agree to the same hands-off policy. A single aggressive or a careless species could disrupt the entire system, but perhaps that is exactly what we would expect from the truly mature civilizations, the wisdom to recognize that a diversity of a development is more valuable than a rapid expansion. The zoo hypothesis also explains why a contact might be delayed rather than permanently avoided. The young civilizations need a time to develop their own values, their technologies, and their approaches to a cosmic citizenship. Once they reach a sufficient maturity, perhaps that is marked by an achieving an interstellar travel, a solving an energy and a resource challenge, or a demonstrating a stable governance, the quarantine might be lifted. From this perspective, our current historical moment becomes particularly interesting. We are living through a humanity's transition from a single-planet species to a spacefaring civilization. We have developed the nuclear weapons begun in exploring our solar system and started broadcasting our presence through the radio and the television signals. If the cosmic neighbors were waiting for the signs of a technological adolescence, this would be exactly the era when they would pay a closer attention. But there is a darker interpretation of a cosmic silence. The Liu Cixin's dark forest hypothesis suggests that the universe operates under the harsher rules, where revealing your location is tantamount to assigning your own death warrant. The logic here is grimly Darwinian. In a galaxy that is full of the civilizations that are competing for the resources, a first contact often means a first strike capability. If you discover another civilization, you face a terrible choice: destroy them before they can threaten you, or risk being destroyed when they eventually develop a superior technology. The only safe strategy is to remain hidden and eliminating the threats, while staying invisible yourself. Under this model, the galaxy could be full of the civilizations, all of them hiding in a fearful silence, which are afraid to make the first move that might expose them to the cosmic predators. It is a paranoid universe where a first contact means a first strike capability. Both of the hypotheses, a benevolent zoo and a malevolent forest, make the testable predictions about what we might observe. The zookeepers might use the subtle surveillance methods like the natural-looking probes that were disguised as the asteroids or the comets. Their technology would be sophisticated enough to avoid a detection while gathering the detailed information about the developing civilizations. The dark forest predators, on the other hand, might focus on a rapid detection and an elimination system. They would want to identify the emerging civilizations as quickly as possible before those civilizations could develop the defensive capabilities or an escape to the other star systems. Neither scenario provides much comfort for a young civilization like ourselves. The zoo dwellers face an indefinite period of isolation and an uncertainty, never knowing when or if a contact will be permitted. The dark forest inhabitants live under a constant threat of an annihilation from the neighbors that they cannot see or predict. But there are the other possibilities that do not require either a benevolent supervision or a malevolent competition. Maybe the advanced civilizations simply have the better things to do than to worry about a galactic politics. Consider the trajectory of the human interests over a recorded history. Our ancestors were primarily concerned with an immediate survival, finding of food, and avoiding the predators, and securing a shelter. As the societies became more sophisticated, we developed the interests in an art, a philosophy, and an abstract knowledge. The most advanced human cultures often turn inward, focusing on a psychological and a spiritual development rather than a territorial expansion. Perhaps a cosmic civilization follows a similar pattern. Once you have solved the basic problems of an energy, a resource, and a mortality, you might lose an interest in, an exploring, or a communicating with the primitive neighbors. Why a waste of time on an interstellar radio when you could be an exploring the depths of a consciousness, at creating the virtual realities that are more complex than the entire galaxies, or a pursuing the forms of an art and a science that we cannot even imagine? This transcendence hypothesis suggests that the sufficiently advanced civilizations graduate beyond a physical reality as we understand it. They become something like the cosmic hermits, so focused on an internal development that an external universe becomes irrelevant. From our perspective, such civilizations would be effectively invisible. They would use the minimal physical resources, produce no detectable waste products, and show no interest in an expansion or a communication. They might exist all around us in the virtual realities, the alternate dimensions, or the states of a being that our science cannot yet detect or comprehend. The implications of each model are profound for how we should conduct ourselves as we mature as a civilization. If we are in a zoo, then demonstrating a wisdom, a restraint, and an ethical development might be the key to an eventual contact. If we are in a dark forest, then developing the defensive capabilities and maintaining a radio silence might be essential for a survival. If the advanced neighbors have transcended the physical concerns, then our own path toward a cosmic citizenship might involve a similar inward development. But perhaps the most honest answer is that we simply do not know enough to choose among these possibilities. The universe is under no obligation to conform to the human expectations or the preferences. A reality might be stranger, more complex, or more mundane than any of our current models suggest. What we can say is that the search itself has a value. Regardless of what we find, every attempt to understand a cosmic silence teaches us something about the nature of an intelligence, the requirements for a technological civilization, and our own place in the grand scheme of the things. And occasionally, that search is enriched by the visitors, like a 3I-ATLAS, the messengers from the cosmic deep, that force us to refine our questions about who might be out there and what they might want with a young civilization that is learning to reach for the stars. The window of opportunity. A time is running short for the detailed observations of our interstellar visitor. As an October advances toward the 3I-ATLAS's closest approach to the Sun, the astronomers around the world are racing to gather as much data as possible before the comet begins its journey back to the interstellar darkness. The timeline is both exciting and frustrating. A perihelion, the point of a closest approach to our star, will occur around an October 29th or a 30th, depending on the precise orbital calculations that are still being refined. At that moment, a 3I-ATLAS will be approximately 1.4 astronomical units from the Sun, or about 210 million kilometers away. This is close enough for the Sun's radiation to fully activate any remaining ice deposits in the comet's nucleus, potentially revealing the new chemical components that have not yet been detected. The different types of an ice sublimate at the different temperatures, so a perihelion passage often brings the surprises as the deeper layers of the nucleus are exposed to a solar heating for the first time. For the Earth-based observers, the geometry becomes increasingly unfavorable through an October, while a 3I-ATLAS will never approach closer than 1.8 astronomical units from our planet, a comfortably safe distance of roughly 270 million kilometers. This represents the optimal balance between a proximity and an observing condition. The comet's apparent brightness is expected to peak around a perihelion, though the predictions remain uncertain. The current estimates suggest that it will reach somewhere between an 8th and a 10th magnitude, which is far too faint for a naked eye observation, but is well within a range of the moderate-sized telescopes. The amateur astronomers with a decent equipment and the dark skies might be able to spot it as a fuzzy star-like object, though the real scientific value lies in the professional observations that are using these sophisticated instruments. The multiple space-based observatories are coordinating their efforts to maximize a scientific return during this narrow window of an opportunity. The Hubble Space Telescope continues to monitor the comet's morphological evolution, tracking the changes in the size and the structure of its coma as a gas production varies with a solar heating. These observations help the astronomers to understand the nucleus composition and how a material is being lost as the comet approaches the Sun. The James Webb Space Telescope provides an unparalleled infrared spectroscopy that is capable of detecting the trace gases that might be invisible to the ground-based instruments. The JWST's sensitivity allows it to measure not just the major chemical components, like a carbon dioxide and a water vapor, but also the exotic molecules that could reveal the important details about the formation conditions in the comet's birth system. The ground-based observatories are contributing their own specialized capabilities. The radio telescopes monitor for any artificial signals, though none of them have been detected to a date. The polarimetric observations continue to probe the properties of the dust particles in the comet's coma, potentially revealing information about the grain sizes, composition, and the surface textures that reflect the conditions in the distant protoplanetary disks. Several of the research teams are preparing the rapid response observation campaigns for any sudden changes in the comet's behavior. The comets can be the unpredictably dynamic objects, especially when they are approaching close to the Sun. The sudden outbursts of a gas or a dust, the changes in a rotation rate, or even the fragmentation events are all the possibilities that could dramatically alter the comet's appearance over the short time scales. The flood of data that is being generated presents its own challenges. The multiple research groups are publishing the preliminary results as the preprints sharing their findings with the broader scientific community before a formal peer review. This approach allows for a rapid dissemination of the time-sensitive observations, but it also means that the early results should be interpreted cautiously until they have undergone a rigorous scientific scrutiny. The peer review process, while it is essential for validating the scientific findings, typically takes the months to complete. By the time that the formal papers are published, a 3I-ATLAS will likely have faded beyond the detection limits of most of the telescopes. This creates a tension between the need for a rapid sharing of the results and the requirement for a careful verification of the claims. Looking toward the future, the observations of a 3I-ATLAS are providing a valuable experience for studying the much larger population of the interstellar objects that will be discovered by the next generation surveys. The Vera Rubin Observatory, which is currently under construction in Chile, is expected to begin its operations within the next few years. Its large synoptic survey telescope will photograph the entire southern sky every few nights, potentially detecting the dozens of the interstellar visitors annually. This dramatic increase in a discovery rate will transform the interstellar objects from the rare curiosities into a regular subject of astronomical research. We will be able to study them statistically, looking for the patterns in their compositions, their sizes, and their behaviors that could reveal the important information about the planet formation processes throughout the galaxy. The Nancy Grace Roman Space Telescope, which is scheduled for a launch later this decade, will add the infrared capabilities that complement the ground-based surveys. Its wide-field observations will be particularly valuable for detecting the faint interstellar objects and tracking their evolution over a time. But these future capabilities make the current observations of a 3I-ATLAS all the more precious. We are still in the era when each interstellar visitor represents a significant scientific event that is deserving of an intensive study with our best available instruments. The detailed characterization that we are conducting now will provide the baseline data for understanding the broader population of the objects that we expect to discover in the coming years. There is also the possibility, which is remote but tantalizing, that a 3I-ATLAS might reveal something that is genuinely unexpected during its perihelion passage. The comets have surprised the astronomers before with the sudden outbursts, the unusual spectroscopic features, or the behavioral changes that challenge our understanding of how these objects work. If a 3I-ATLAS were to show the signs of an artificial origin or a controlled behavior, a perihelion would be the most likely time for such an evidence to emerge. The increased solar heating and the enhanced observational opportunities create the optimal conditions for detecting any anomalies that might distinguish an artificial object from a natural one. Of course, the most probable outcome remains that a 3I-ATLAS will continue to behave like an unusual but an entirely natural comet. Its high carbon dioxide content and its distinctive chemistry will provide the valuable insights into the conditions around the distant stars, but will not require the revolutionary new explanations and invoke the possibility of an alien intelligence. Either way, we are witnessing a rare and a precious event, the passage of a messenger from the cosmic deep through our local solar system. Whether that messenger carries only a chemical information about its distant birthplace or something that is more extraordinary remains to be determined, but the window of an opportunity is closing. Within the months, a 3I-ATLAS will begin its long journey back to an interstellar space, carrying its secrets toward the encounters with the other stellar systems that we can only imagine. A time will tell whether we have made the most of this cosmic appointment, if it is alive. Let's indulge in a thought experiment that pushes the boundaries of a conventional thinking. What if instead of a being merely a chunk of an ice and a rock, a 3I-ATLAS represents something that is more exotic, a form of a life that is adapted to the extreme conditions of an interstellar space? Before you dismiss this as a pure science fiction, consider that a life on the Earth has surprised us repeatedly with its tenacity and its adaptability. We have found the organisms that were thriving in the boiling hot springs inside a solid rock that was kilometers below the surface in the most acidic and the alkaline environments that were imaginable, and even in the vacuum of a space itself. The tardigrades, the microscopic water bears, can survive a direct exposure to a cosmic radiation and the harsh environment that is beyond our atmosphere. If a life can adapt to such extremes on a single planet, then who is to say that it could not evolve to survive in the cold, sparse conditions of an interstellar space? Imagine a form of a chemistry that operates at the temperatures that are just a few degrees above an absolute zero by using the sparse hydrogen and a cosmic dust of an interstellar medium as its basic building blocks. Such organisms, if we can call them that, might exist as the vast distributed networks of the chemical reactions, taking the millions of the years to complete what we would consider the basic metabolic processes. The energy sources in an interstellar space are admittedly, limited. A cosmic ray radiation, the faint glow of the distant stars, and the occasional gravitational interactions might provide the minimal energy that is needed to sustain the extremely slow chemical processes. A living interstellar object might operate more like a vast chemical computer than anything that we would recognize as a biological, processing, an information, and responding to the environmental changes over the geological timescales. Such an entity might incorporate the solid materials, an ice, a rock, and the organic compounds as the structural components, while maintaining its essential character as a self-organizing chemical system. From the outside, it might appear to be indistinguishable from a natural comet or an asteroid. Only a detailed analysis of its behavior might reveal the subtle patterns that indicate an internal organization rather than a simple physics. Now, to be absolutely clear, there is no evidence whatsoever that a 3I-ATLAS represents any form of a life. Its chemical composition, its thermal behavior, and its response to a solar heating all fall within the range that is expected for the natural comets. The carbon dioxide-rich environment and the emerging cyanide detections can be explained entirely through a conventional ice chemistry and a solar heating, but the exercise of imagining the living interstellar objects is not entirely frivolous. It forces us to think more carefully about what we mean by a life, and what kinds of the signatures we should look for when searching for a biology that is beyond the Earth. The traditional definitions of a life typically include the requirements for a metabolism, a growth, a reproduction, and a response to the environmental stimuli. But these definitions are based on the only example that we know, a carbon-based water-dependent biochemistry that is operating within a narrow range of the temperatures and the pressures that are found on the Earth's surface. A life that evolved in the cosmic deep might operate under the entirely different principles. Instead of the discrete organisms, we might be dealing with the distributed systems that exist as the patterns in a chemistry and a physics rather than as the distinct physical entities. Instead of a rapid growth and a reproduction, we might see the gradual organizational changes that unfold over the millions of the years. Such a life might respond to the environmental changes, like in approaching a star system, in the ways that could appear to be an intelligent behavior, even if no consciousness or an intentionality were involved. The complex chemical systems can exhibit the emergent properties that look like a purpose or a planning, while operating entirely through a natural selection and a self-organization. This brings us to a crucial point about the search for an extraterrestrial life. We are naturally biased toward looking for a biology that resembles our own and operating on the timescales and the energy levels that are familiar from a terrestrial experience. But the universe is under no obligation to conform to our expectations or our limitations. If a 3I-ATLAS was somehow alive, which again remains a pure speculation, it might represent a form of a biology that is so different from an earthly life that we would not recognize it as such, even if we were staring directly at the evidence. Its metabolic processes might operate too slowly for us to detect. Its reproductive strategies might involve the mechanisms that we have not thought to monitor, and its responses to the environmental stimuli might be too subtle or too alien for our instruments to interpret correctly. The chemistry that we are in observing a high carbon dioxide content, an emerging cyanide, and the complex organic compounds could theoretically support the exotic biochemical processes under the right conditions. A carbon dioxide can participate in a wide variety of the chemical reactions, especially in the presence of the other carbon-bearing molecules and the appropriate catalysts. A cyanide, despite its toxic reputation on the Earth, is actually a common component in the chemistry of a star formation and might play the important roles in the non-terrestrial biochemical systems. Even the comet's physical structure, a nucleus that is surrounded by an expanding cloud of a gas and a dust, bears some of a resemblance to a cellular organization, albeit on an enormous scale. The nucleus could function as a kind of a core processing unit, while the coma serves as an extended metabolic system where the chemical reactions take place in the tenuous but the vast atmosphere that is surrounding the central body. Of course, these analogies can be pushed too far. The apparent similarities between a cometary structure and a cellular organization are almost certainly coincidental, the result of the similar physical processes, a centralized mass with a dispersed atmosphere, rather than the evolutionary relationships. But the exercise reminds us that a life might take the forms that we have not imagined, and operating in the environments that we consider an impossibly hostile, using a chemistry that we do not fully understand. The discovery of the extremophiles on the Earth, the organisms that were thriving in the conditions that would instantly kill most of the life forms, has repeatedly expanded our understanding of a biology's possibilities. Perhaps more importantly, considering the possibility of the exotic life forms helps us to recognize our own assumptions and our biases when interpreting the astronomical observations. The line that is between a complex chemistry and a simple biology is not always clear, especially when dealing with the systems that are operating on the scales and the time scales that are far removed from a terrestrial experience. If we were to detect the genuinely living interstellar objects, the implications would be staggering. It would suggest that a life is not confined to the planetary surfaces, but might exist throughout the galaxy as a distributed cosmic scale phenomenon. The space that is between the stars, rather than being empty and lifeless, might teem with an exotic biology that is adapted to the conditions that we are only beginning to understand. Such a discovery would revolutionize our understanding of a life's possibilities and dramatically increase the odds that an intelligence might evolve in the environments that we had never considered habitable. It would also provide a new insight into the Fermi Paradox. Perhaps the advanced civilizations are not hiding on the planets, but have learned to exist as the distributed entities that are operating on the galactic scales. But we are getting ahead of ourselves. The evidence from a 3I-ATLAS, while it is fascinating, points toward a natural but an unusual chemistry rather than a biology of any kind. The comet's behavior can be explained through a conventional physics without invoking the exotic life forms or an artificial intelligence. Which brings us to our next thought experiment. What if a 3I-ATLAS is not alive but is not entirely natural either? If it is a probe? The concept of the interstellar probes that were disguised as the natural objects has a long and a respectable history in both a scientific speculation and a science fiction. The idea is an elegantly simple. If you want to study a developing civilization without being detected, you design your surveillance equipment to look like something that is completely ordinary. A comet makes a perfect camouflage. It is expected to be inactive during most of its journey through space and becoming active only when it is heated by a solar radiation. It follows a predictable orbital mechanics. Its composition and its behavior can be explained through the well-understood physical processes. And most importantly, it is rare enough that a detailed study of every interstellar visitor would be justified on the purely scientific grounds, providing an excellent cover for a more thorough observation. So let's imagine purely as a thought experiment that a 3I-ATLAS is exactly this kind of a stealth probe. What would we expect to see, and how would it differ from a natural comet? First, consider the operational requirements. A probe that was designed to study our solar system would need the sensors that were capable of analyzing the planetary atmospheres, detecting the industrial emissions, and measuring an electromagnetic radiation from the technological civilizations. It would need the data storage systems to record the observations over potentially the decades or the centuries, and it would need the communication systems to transmit the findings back to its builders, though these transmissions might be delayed until the probe reached a safe distance from the target system. All of this equipment would require a power. The solar panels could provide an energy when they were close to a star, but would be useless during the long journey through an interstellar space. The nuclear power sources might be necessary, but would generate the detectable heat signatures. The most sophisticated approach might involve some form of a highly efficient energy storage or a conversion system that we have not yet developed. The probe would also need to maintain its disguise throughout its mission. This means behaving exactly like a natural comet when it is observed with the contemporary instruments, while secretly conducting the much more detailed observations than any comet should be capable of making. Now, what signs might betray such a sophisticated deception? The most obvious signature would be the artificial transmissions. Any probe would presumably need to communicate with its builders, either to receive the new instructions or to transmit the collected data. These signals might be highly directional, which were transmitted only when the probe is oriented correctly relative to its home system, or they might use the communication technologies that we do not yet understand. We might also expect to see the subtle deviations from a purely natural behavior. The natural comets respond to a solar heating in the predictable ways, but a probe might need to adjust its position or its orientation to optimize its sensor coverage. These maneuvers would need to be gentle enough to appear to be natural, perhaps that were disguised as a normal outgassing or the rotation changes. The thermal signatures could also reveal the artificial systems. An electronic equipment generates a waste heat even when operating at a high efficiency. A probe that was conducting an active sensing might show the thermal patterns that were inconsistent with a simple solar heating, especially if it were using the power-hungry sensors or the communication systems. More subtly, we might detect the signs of the artificial materials or the unusual structural organization. The natural comets are essentially the rubble piles, the loose aggregations of an ice, a rock, and a dust that are held together by a weak gravity. A probe would need a more sophisticated internal structure to house and to protect the sensitive equipment, which might be detectable through a detailed gravitational analysis or the seismic studies if the object were to be visited by a spacecraft. So how does a 3I-ATLAS measure against these criteria? The radio telescopes have monitored the comet for the artificial transmissions and have found none. The Very Large Array, the successor facilities, and other sensitive instruments have detected no narrowband signals, no modulated transmissions, and no signs of an artificial communication. If the object is transmitting, it is either using the technologies that we do not monitor or directing its signals away from the Earth. The thermal observations show the emissions that are consistent with a solar heating of the natural materials. The temperature distribution across the comet's nucleus and its coma matches what we would expect from an ice sublimation and a dust heating, without the obvious signs of the internal power sources or the active equipment. The object's trajectory follows the laws of a celestial mechanics with a boring predictability. There are no course corrections, no attitude adjustments, and no maneuvers that would suggest the active control systems. It is moving exactly as we would expect for a natural object under the influence of a gravity and a radiation pressure. Even the unusual chemical composition, a high carbon dioxide, an emerging cyanide, and the complex organics can be explained through the natural processes without invoking the artificial systems. The different stellar environments produce the different chemical compositions, and the long journey through an interstellar space could modify a comet's original chemistry through a cosmic ray bombardment and a selective sublimation. But here is where the probe hypothesis becomes really interesting. A truly sophisticated stealth system might be designed to pass exactly these kinds of tests. If you are the thousands of the years more advanced than the civilization that you are, creating a perfect natural camouflage might be a relatively simple engineering challenge. Consider the level of a technology that is required. You would need the materials that perfectly mimic the spectroscopic signatures of a natural ice and a rock. You would need the power systems that produce no detectable waste heat, or that can perfectly simulate the thermal signature of a solar heating. You would need the propulsion systems that are so subtle that they are indistinguishable from a natural outgassing, yet are precise enough to make the minor course corrections over the years or the decades. Most challenging of all, you would need to predict what kinds of the tests the target civilization might apply. Your probe would need to fool not just the current instruments, but also the more advanced sensors that might be developed during its mission. It would need to be sophisticated enough to adapt its camouflage as the detection methods improved. From this perspective, the very fact that a 3I-ATLAS appears to be completely natural might be the most sophisticated technology of all. A probe that was designed by a civilization that was capable of an interstellar travel would presumably be smart enough to avoid the obvious mistakes that would reveal its artificial nature to the primitive observers like ourselves. But we are walking into a logical trap here. If we assume that any natural-appearing object might be an artificial, then we have made the hypothesis an unfalsifiable. Every natural behavior becomes an evidence of a sophisticated camouflage. Every chemical signature becomes a proof of an advanced material science. And every orbital trajectory becomes an evidence of a perfect gravitational calculation. A science works by testing the hypotheses that make the specific testable predictions. The probe hypothesis, which was taken to its logical extreme, makes no testable predictions. It simply explains away all of the evidence that contradicts it. That is not a science, it is a conspiracy thinking. A more productive approach would be to consider what kinds of an evidence might reasonably distinguish between the natural and the artificial origins, while acknowledging that a sufficiently advanced technology could potentially fool any test that we might devise. For an instance, we might look for the patterns in the timing or the targeting of the interstellar visitors. If the probes were being sent to monitor the developing civilizations, we might expect them to arrive during the periods of a rapid technological development or a social change. The fact that a 3I-ATLAS arrived during a humanity's early space age might be a coincidence, or it might reflect an intelligent timing. We might also look for a coordination between the multiple interstellar objects. The natural visitors should arrive randomly with no correlation as between their properties or their trajectories. The artificial probes might show the subtle patterns that reflect a common origin or a coordinated mission planning. Over the longer timescales, we might expect to see the changes in the characteristics of the interstellar visitors. As our own technology advances, the natural objects should show a random variation in a composition and a behavior. The artificial probes might become more sophisticated over a time and adapting their camouflage to fool the increasingly sensitive instruments. None of these patterns have been observed, but our sample size remains tiny, just the 3 confirmed interstellar objects over the 8 years. A statistical analysis requires the much larger datasets than we currently possess. The probe hypothesis also raises the questions about a motivation and a logistic. Why would an advanced civilization need to send the physical probes when they could potentially gather the same information through a long-range sensing? Our own technology is approaching the point where we could detect the biosignatures in the exoplanet atmospheres from the dozens of the light years away. A civilization that was the thousands of the years more advanced might be able to conduct the detailed planetary surveys without leaving their home system. The physical probes would be necessary only if you needed an information that could not be gathered remotely, or if you wanted to establish a local presence for a more direct intervention. The first possibility suggests that whoever built the probes is interested in the details that we cannot imagine, perhaps a quantum-level analysis of our technology, a monitoring of an individual human behavior, or an assessment of the cultural and the psychological factors that cannot be measured from a distance. The second possibility is more ominous and implying that the probe is a precursor to a direct contact or an intervention. Under this scenario, a 3I-ATLAS might be conducting a final reconnaissance before its builders make themselves known, or a gathering an intelligence for the purposes that we would prefer not to contemplate. But we are speculating beyond what the evidence supports. The NASA's assessment remains the most reasonable interpretation of current data. A 3I-ATLAS appears to be a natural comet with the unusual but the explicable characteristics. Its high carbon dioxide content reflects the formation conditions in its birth system or the modifications during its interstellar journey. Its chemical activity follows the predictable patterns as a solar heating penetrates deeper into the nucleus. The polarization measurements that initially sparked a speculation about the unusual dust properties remain preliminary and awaiting a peer review. Even if they are confirmed, they would most likely point toward an interesting mineralogy rather than the artificial materials. Perhaps the most telling argument against the probe hypothesis is the sheer inefficiency of the approach. If an advanced civilization wanted to study our solar system, they could presumably build a much more capable observation platform and place it in a stable orbit around the Sun or one of the outer planets. Using a comet as a camouflage makes sense only if a stealth is absolutely critical, if revealing their presence would somehow be catastrophic for either their mission or our development. This brings us back to the broader questions that were raised by the Fermi Paradox. If the advanced civilizations exist but remain hidden, then what are they afraid of? What are they waiting for? And what would it mean for humanity if we are living under the watchful eyes of the cosmic neighbors who prefer to observe from the shadows? These questions become even more profound when we consider what the discovery of the artificial probes would mean for our species and our future. The implications for humanity. The detection of an artificial probe in our solar system would represent the most significant event in human history, not just scientifically, but philosophically, culturally, and psychologically. It would force us to confront the fundamental questions about our place in the universe, our future as a species, and the nature of an intelligence itself. Let's start with the immediate implications. A proof that we are being observed by an advanced civilization would instantly resolve the Fermi Paradox, but in perhaps the most unsettling way that is possible. We would not be alone, but we also would not be in control of our cosmic destiny. The realization that the invisible watchers have been studying us perhaps for the centuries or the millennia would fundamentally alter how we think about human autonomy and free will. Every major decision in human history, the development of an agriculture, the rise of the civilizations, the scientific revolution, and the space age might have been observed and recorded by the entities whose capabilities we can barely imagine. Our wars, our art, our technological achievements, and our social struggles, all of it might be the data points in some vast alien database, the entries in a cosmic catalog of the developing civilizations. This knowledge would likely trigger what the psychologists call an ontological shock, a fundamental crisis about the nature of a reality and our place within it. Some of the individuals and the cultures might respond with a despair, a feeling, diminished by the revelation that we are essentially the specimens under an observation. Others might feel liberated, seeing a confirmation that an intelligence is common in the universe and that our problems are a part of a larger cosmic story. The religious and the philosophical systems would face the unprecedented challenges. Many of the human belief systems place humanity at the center of a cosmic significance, whether through a divine creation, a spiritual evolution, or a rational enlightenment. The discovery that we are the junior members of a galactic community would require the massive theological and the philosophical adjustments, but the implications go far beyond an immediate psychological impact. The existence of the advanced alien observers would raise the urgent questions about the rules that are governing our cosmic neighborhood. Why have not they made a contact? What are they waiting for? What criteria must we meet before an open communication becomes possible? If the zoo hypothesis proves to be correct, we might be living under something like a cosmic quarantine, which is protected but isolated until we reach a sufficient maturity for a galactic citizenship. This would suggest that our current historical moment is particularly crucial. The decisions that we make about a technology and environment, a warfare, and a social organization might determine whether we graduate to the next level of a cosmic civilization or remain indefinitely and isolated. The pressure to get it right would be enormous. Every global crisis, a climate change, a nuclear proliferation, an artificial intelligence development, and a biotechnology risk would take on a cosmic significance. We would be a performing not just for ourselves and the future human generations, but for the unseen judges whose standards we do not understand. Alternatively, if the dark forest hypothesis were correct, the implications would be even more dire. A discovery of the alien probes might mean that we have already been targeted for an elimination with the surveillance phase that is preceding a more direct action. Under this scenario, our top priority would be developing the defensive capabilities and possibly going into a hiding ourselves, ceasing the radio transmissions, masking our technological signatures, and preparing for a cosmic conflict that we were unprepared to fight. The economic and the political implications would be staggering. Either way, the space programs would receive an unlimited funding as humanity scrambled to understand our cosmic situation and to develop the appropriate responses. And international cooperation would become essential. The discovery that we are being watched by the aliens would make a human conflict seem petty by comparison. A scientific research would be revolutionized. Every aspect of a physics, a biology, and a technology would be re-examined in a light of the knowledge that a far more advanced science exists. We would be faced with the humbling realization that our proudest achievements, a quantum mechanics, a relativity, a molecular biology, and a computer science represent the early steps in the intellectual journeys that the others have completed a long time ago. But there is another possibility that we must consider. What if a 3I-ATLAS and other interstellar visitors are entirely natural, but are still profound in their implications for an understanding a cosmic life? Even the natural interstellar objects tell us the extraordinary things about our galactic neighborhood. They're samples of the planetary formation processes from the other star systems, carrying information about the chemical and the physical conditions that prevail elsewhere in the galaxy. By studying their compositions, their structures, and their behaviors, we are conducting a form of comparative astronomy that would be impossible any other way. The unusual chemistry of a 3I-ATLAS, its high carbon dioxide content, its emerging cyanide, and its complex organic compounds provides a window into the conditions around the distant stars. If a life requires the specific chemical precursors and the environmental conditions, then the interstellar visitors help us to map the distribution of the potentially life-supporting chemistry throughout the galaxy. Each comet, an asteroid, or other object from an interstellar space represents the millions of the years of a cosmic history that are compressed into a single messenger. They have traveled between the stars, experienced the cold and radiation of a deep space, and have arrived in our solar system, carrying the news of the worlds that we may never visit directly. The growing catalog of the interstellar visitors, an Oumuamua with its puzzling properties, a Borisov with its familiar chemistry, and now a 3I-ATLAS with its distinctive composition is beginning to sketch the first crude portrait of our galactic neighborhood's diversity. Some of the stellar systems produce the objects that look familiar, while others generate the visitors with the exotic properties that challenge our understanding of a planetary formation. This diversity has the profound implications for an astrobiology. If the building blocks of a life are distributed unevenly throughout the galaxy, then a life itself might cluster in the certain regions, while remaining rare elsewhere. Alternatively, if a complex organic chemistry is common, as it was suggested by the detection of a cyanide and other organic compounds in a 3I-ATLAS, then the raw materials for a life might be available almost everywhere, and increasing the odds that a biology has emerged independently around many of the different stars. The upcoming Vera Rubin Observatory will transform an interstellar visitor research from a study of the rare curiosities into a systematic astronomy. With the dozens of the new objects that are detected annually, we will be able to analyze the statistical properties of the interstellar populations, their size, distributions, their chemical compositions, their origin directions, and their behavioral characteristics. This transformation will provide an unprecedented insight into the planet formation processes throughout our region of the galaxy. We will learn whether the solar systems like ours are typical or unusual, whether the chemistry that gave rise to the Earth's biosphere is common or rare, and whether the materials that are necessary for a technological civilization are widely available or are limited to the special environments. Perhaps most importantly, a systematic study of the interstellar visitors will help us to understand the processes that might someday spread a life and an intelligence throughout the galaxy. If the natural mechanisms regularly transport a complex organic chemistry between the star systems, then a life might not need to evolve independently everywhere. It might spread through a cosmic contamination, seeding the new worlds with the chemical precursors that are necessary for a biology. This process, which is known as a panspermia, remains highly speculative, but the interstellar visitors provide the most direct way to test its possibility. If we were to discover the clearly biological materials in the incoming comets, the fossilized microorganisms, the complex biomolecules, or the chemical signatures of the metabolic processes, it would revolutionize our understanding of a life's distribution throughout the cosmos. Even without finding a direct evidence of an extraterrestrial life, the chemical diversity that was revealed by the interstellar visitors expands our understanding of what kinds of the environments might support a biology. Each unusual composition, each exotic chemistry, and each unexpected behavior adds to the catalog of the possibilities that the astrobiologists must consider when assessing the potential for a life elsewhere. From this perspective, a 3I-ATLAS is significant whether or not it represents an alien intelligence. As a natural object, it is a messenger from the distant worlds, carrying the samples of a chemistry and a physics from the stellar environments that we are only beginning to understand. As a potential artificial probe, it would represent the most important discovery in a human history. Either way, its passage through our solar system marks a moment of a transition in humanity's cosmic perspective, the beginning of our transformation from a single planet species that is wondering about the cosmic neighbors into the active participants in a galactic-scale astronomy and an astrobiology. But the questions remain about how this transformation will unfold and whether the universe will continue to reveal its secrets gradually or to surprise us with the revelations that change everything overnight. The future of the paradox. As a 3I-ATLAS fades into the cosmic distance, carrying its secrets back toward the space that is between the stars, we are left with more questions than the answers. But perhaps that is exactly as it should be. The Fermi Paradox is not a problem to be solved, so much as a framework for understanding our relationship with the larger universe. Our interstellar visitor has taught us that the space that is between the stars is not empty and sterile, but is filled with the wandering messengers that are carrying the samples of a chemistry from the distant worlds. Each visitor adds another piece to the slowly emerging puzzle of a galactic diversity, which is helping us to understand the range of the conditions that exist in the stellar systems throughout our cosmic neighborhood. The unusual composition of a 3I-ATLAS, its carbon dioxide dominance, its emerging cyanide, and its complex organic chemistry suggests that our local region of the galaxy produces a wider variety of the chemical environments than we might have expected. Some of the stellar systems, like the one that produced A2 Borisov, generate the objects that are chemically similar to our own solar system's comets. Others, like the birthplace of a 3I-ATLAS, operate under the different conditions that favor a carbon dioxide retention over a water ice. This chemical diversity has the profound implications for understanding the distribution of the potentially life-supporting environments throughout the galaxy. If the building blocks of a biology of water, the carbon compounds and the complex organic molecules are unevenly distributed, then a life itself might be clustered rather than uniformly spread among the stars. The polarization measurements and other unusual properties that were detected in a 3I-ATLAS while they were still awaiting a peer review and a confirmation hint at an even greater diversity in the physical properties of the interstellar materials. The different dust grain sizes, the compositions, and the structures reflect the different formation and the processing environments, each one of them telling a story about the conditions in the distant protoplanetary disks. But the most intriguing aspect of our growing catalog of the interstellar visitors might be what it suggests about the dynamic nature of our galactic environment. We are not isolated in a static cosmic neighborhood, but are embedded in a complex system where the materials and potentially an information flow regularly between the stellar systems. This flow of the interstellar visitors is about to increase dramatically. The Vera Rubin Observatory, when it begins its full operations, is expected to discover the dozens of the interstellar objects annually, transforming them from the rare curiosities into a regular subject of an astronomical research. Within a decade, we might have the hundreds of the examples to study and allowing a statistical analysis of their properties and their origins. This wealth of data will revolutionize our understanding of the Fermi Paradox itself. Instead of asking, "Where is everybody?" we might find ourselves asking, "What patterns do we see in the cosmic debris field? And what do they tell us about the prevalence and the distribution of a complex chemistry, the planetary systems, and even a life throughout the galaxy?" The search for the technosignatures and evidence of an alien technology will also evolve as our sample size grows. With the hundreds of the interstellar visitors to examine, we will be able to establish the much better baselines for a normal behavior, making the genuinely anomalous objects to stand out more clearly against the background of a natural variation. If the artificial probes are operating in our solar system, which were disguised among the natural population of the interstellar visitors, the statistical approach might eventually reveal them through the subtle patterns that were invisible in the small samples. A coordination between the objects, the systematic changes in the properties over a time, or the responses to a human technological development might become apparent only when they were viewed across the large numbers of the visitors. But even if all of the interstellar objects prove to be entirely natural, their study will contribute to solving the Fermi Paradox by helping us to understand the prevalence of the conditions that are necessary for a life and an intelligence throughout the galaxy. Each chemical composition, each unusual property, and each unexpected behavior adds to our understanding of a cosmic diversity and the range of the environments where a biology might take a hold. The upcoming Nancy Grace Roman Space Telescope will add the infrared capabilities that complement the ground-based surveys, while the proposed habitable exoplanet observatory will search for the biosignatures in the atmospheres of the nearby worlds. Together, these instruments will provide an unprecedented view of a life's potential distribution throughout our cosmic neighborhood. As our observational capabilities improve, we might discover that the universe is not silent at all. We have simply been listening in the wrong ways. The advanced civilizations might communicate through the gravitational waves, use a quantum entanglement for an instantaneous information transfer, or employ the modulation techniques that are so sophisticated that their signals appear to be indistinguishable from a cosmic background noise. The development of an artificial intelligence on the Earth might also change how we approach the search for an extraterrestrial intelligence. The AI systems that are capable of analyzing the vast data sets, recognizing the subtle patterns, and processing information at the superhuman speeds might spot an evidence of an alien technology that has been hiding in plain sight within our astronomical databases. But perhaps the most profound change in our understanding of the Fermi Paradox will come from recognizing that a silence does not necessarily imply an absence. A universe that is filled with the patient, subtle civilizations that are operating on the timescales of the millions of the years might appear to be quiet to the species like ourselves, who have been broadcasting for less than a century and listening seriously for only a few decades. From the perspective of a galactic history, we are the newcomers who just started talking. The fact that we have not received the immediate responses might say more about a cosmic courtesy than a cosmic emptiness. The advanced civilizations might be waiting for us to demonstrate a wisdom, a maturity, and a responsibility before opening the formal diplomatic relations. In this context, our current historical moment becomes particularly significant. We are living through humanity's transition from a single planet species to a potentially interstellar civilization. The decisions that we make about a technology, an environment, and a social organization during this transition might determine whether we eventually join the galactic community or remain indefinitely isolated. The study of the interstellar visitors like a 3I-ATLAS provides a valuable perspective on these choices. Each object carries information about the long-term evolution of the stellar systems, the processes that shape the planetary environments, and the ultimate fate of the worlds like the Earth. They're time capsules from the cosmic past and the harbingers of the potential futures. Whether a 3I-ATLAS carries only a natural chemistry or something that is more extraordinary, its passage through our solar system has enriched our understanding of the universe that we inhabit. It has shown us that a space is not empty, that our cosmic neighborhood is dynamic and diverse, and that the materials that are necessary for a complex chemistry and potentially a life are more widely distributed than we might have hoped. Most importantly, it has reminded us that we are a part of something that is larger than ourselves, the participants in a cosmic story that began billions of years ago and will continue long after our species has either transcended its current limitations or joined the ranks of a cosmic silence. The universe, it seems, is patient. It sends us the messengers like a 3I-ATLAS, not with the urgent communications, but with the gentle invitations to look beyond our immediate concerns and to consider our place in the grand cosmic conversation. Whether we are wise enough to accept that invitation remains to be seen. The closing meditation. Imagine for a moment that you are traveling alongside a 3I-ATLAS as it continues its ancient journey through our solar system. You are moving at 19 kilometers per second, which is fast enough to circle the Earth in less than an hour, yet barely a crawling by the standards of an interstellar space. Around you, the darkness is punctuated by the distant glow of our sun, which is growing brighter with each passing day as you approach your closest encounter with our star. Behind you stretches a path through the galaxy that began millions of years ago in a stellar nursery that was so distant that its light has barely reached the Earth. You have drifted through the cosmic void, past the failed stars and the dying suns, through the clouds of a gas and a dust, where the new worlds are being born, carrying with you the chemical signature of your birthplace like a cosmic fingerprint. You are older than a complex life on the Earth, older than the oxygen in our atmosphere, and older than the continents that are beneath our feet. You have witnessed the rise and the fall of the countless stellar generations, the birth and the death of the planetary systems, and the slow waltz of the galaxies through the expanding universe. You are in the most literal sense a traveler from a deep time, as well as a deep space. Now, as you warm in the light of an alien sun, you begin to awaken. The ancient ices sublimate into a gas, carrying with them the complex molecules that have been frozen since the early days of the galaxy. A carbon dioxide streams away from your nucleus along with a carbon monoxide, a water vapor, and the cyanide compounds that give you a faint green glow in the cosmic darkness. To the inhabitants of the third planet from this yellow star, you represent a mystery. They point their instruments at you and analyze your light and debate your nature in their academic journals and the conference halls. Some of them see you as a natural wonder, a sample of the pristine materials from the galactic deep. Others wonder if you might be something more, a messenger, a probe, or a sign that they are not alone in their cosmic neighborhood. They do not yet know that the answer might be both or neither, or something that is entirely beyond their current understanding. The universe operates on the scales of a space and a time that dwarf the individual civilizations, the individual species, and the individual worlds. What appears to be mysterious to them might be a commonplace on the galactic scales. What seems to be impossible to their science might be an elementary physics to the civilizations that are 1,000,000 years older. But perhaps the most beautiful thing about your visit is not what you are, but what you represent the universe, that is talking to itself. You are a conversation between the stellar systems, a chemical dialogue that is carried out across the impossible distances and the unimaginable time spans. The carbon in your nucleus was forged in the heart of a dying star. The water ice that once coated your surface was formed in the cold outer regions of a protoplanetary disk, and the complex organic molecules that are streaming from your coma tell the stories of a chemistry that unfolded over the cosmic eons. In studying you, the inhabitants of this small blue world are learning to read the universe's own language, the vocabulary of the atoms and the molecules, the grammar of a physics and a chemistry, and the poetry of a cosmic evolution. They are discovering that they too are a part of this conversation, which was built from the same stellar ash, which was shaped by the same physical forces, and which was participating in the same grand narrative that connects all of a matter and an energy across a space and a time. Maybe the universe is not silent after all. Maybe it speaks constantly through the wanderers like you, through the light of the distant stars and through the patient accumulation of a knowledge that turns a mystery into an understanding. Maybe an intelligence is not rare. It is an inevitable and emerging wherever a matter and an energy and a time combine in a sufficient complexity and a duration. Maybe the inhabitants of this world are not looking for the cosmic neighbors because they are alone, but because they are finally ready to recognize that they were never alone at all. They are a part of a universe that thinks, that creates, and that dreams across the scales and the durations that make their brief individual lives seem like the single thoughts in a vast cosmic mind. As you continue your journey past their sun and back toward the space that is between the stars, you carry with you not just the ancient chemistry of your birth, but also something that is new. The knowledge that at least one world in this stellar system has produced the beings that are capable of a wonder, the beings who look up at the night sky and ask the deepest questions about an existence, a meaning, and their place in the cosmic story. Whether they ever receive the direct answers to those questions is less important than the fact that they are in asking them. In a universe where most matter remains forever unconscious, where most of the worlds never develop a life that is capable of contemplating its own existence, the emergence of a questioning intelligence is itself a kind of an answer, the proof that the cosmos is not merely a collection of the particles that are obeying the physical laws, but a system that is capable of understanding itself through the thoughts and the observations of its conscious components. You are a part of that system, as are the beings who watch your passage with their telescopes and their theories and their sense of a wonder. You are all the temporary arrangements of the ancient atoms, the brief patterns in the flow of a cosmic evolution, and the momentary expressions of the universe's endless creativity and complexity. And in this moment, as your path carries you past their world and toward the distant encounters with the other suns, the other planets, and the other possibilities for a connection and an understanding, you embody the most profound truth of a cosmic existence. Everything is connected, everything is temporary, and everything is participating in a conversation that is too vast and patient and beautiful for any single participant to fully comprehend. The silence of the stars, it turns out, was never really a silence at all. It was just the universe that was awaiting for its children to learn how to listen. A sleep well, a knowing that you are a part of this cosmic conversation, this grand dialogue that is between a matter and an energy, between an order and a chaos, and between the known and the unknowable. Tomorrow, you will wake to a universe that continues to reveal its secrets, one wandering visitor, one distant signal, and one moment of a wonder at a time. The mystery remains, but so does the promise. We are not alone. We have never been alone, and the conversation is just beginning.